Hello, everybody, and welcome to today's webinar presentation, Deploy a Cloud-Native Database on Kubernetes with CockroachDB, brought to you by Cockroach Labs. I would like to introduce you to our presenters. First, Jim Walker. Jim is a recovering developer turned product marketer and has spent his career in emerging tech. He believes product marketing is a strategic go-to-market function in growth companies and helps organizations translate complex concepts into a compelling and effective core narrative and market strategy. The list of startups he has had full-time roles in include ServeGate, Vontu, Initiate Systems, Talend, Hortonworks, Everstring, CoreOS, and his current gig, Cockroach Labs. And now for our second presenter, Keith McClellan. Keith is Director of Partner Solutions Engineering at Cockroach Labs. Keith's responsible for building CockroachDB-based solutions with our largest technology partners, including several Kubernetes distributions and the broader open source ecosystem. Prior to Cockroach Labs, he held leadership positions in cloud-native and big data companies, including DataStax, Mesosphere, and Platforma.
Great, thank you so much. So again, let me get my slides moving here. My name is Jim Walker. Again, I'm VP of Product Marketing at Cockroach Labs. You know, Keith and I both share a common lineage in that, you know, we spent a fair amount of time working in kind of the orchestration world and, you know, thinking about Kubernetes a lot. And, you know, I think when we both landed at Cockroach Labs, we just both basically said, wow, man, there's a database that was built for this new world. And you know, I hope today our passion for Kubernetes and for databases comes out. You know, I think it's something that's near and dear to both of our hearts. And I don't know, I mean, as far as work goes, we feel like we're working on some pretty cool stuff here. So again, I just wanted to, you know, just say again, thank you everybody for taking time today to join us. And I do hope this is compelling and helpful. That said, you know, we're here for you. We're happy to answer questions and talk through things or clarify things along the way. So please do, by all means, you know, post questions into the QA panel, throw them into chat, whatever it is, because we're happy to kind of interact and do this whole thing. Finally, I'm going to have some slides today, but hopefully the slides are there to provide context for kind of how databases are thought about within the context of Kubernetes. And, you know, I don't have a whole lot of slides. It's a lot of building slides here, but hopefully it's there to help augment and really show off the stuff that we're going to show in the demos. You know, I would love to see some fingers on keyboard time. And so I'm gonna get over into Keith doing a demo, and I'm gonna provide the context and slides. So with that, Keith, you ready to go, buddy?
Absolutely.
Did I miss anything? That was a decent intro this time around, huh?
Yeah, I mean it's getting easier. We've been doing these virtually and remote now for a couple of months, so I think we're finally starting to get the hang of it.
Right. And so, yeah, like I think I just so used to being on Zoom now that my natural or go-to meeting or whatever, my natural state is this now. So, all right, so Kubernetes, you know, Kubernetes really emerged over the past couple of years. You know, there was kind of a war, if you will, between some of the orchestration tools, you know, Mesos and Swarm and even Nomad for that matter. And it just really seems over the past couple of years, Kubernetes has really kind of bubbled up to the top as kind of the de facto standard for the way in which people kind of manage and deal with containers at mass scale, containerized applications. And you know, Kubernetes being, you know, a kind of all exhaust from Google was really built for these kind of large scale systems. But at the core of what it is, it really kind of break it down into two things. You know, I mean, I've been trying to simplify Kubernetes for years. It basically allows you to scale your applications up and down very elegantly and ensures that they're always on. That's pretty much it. You know, there's so many features, and I could get so deep into the depths of configuration of Kubernetes, but you know, ultimately at the top level, that is really what it allows to do. As we started containerized applications, you know, how do we scale those things? How do we manage them? How do we deploy them across multiple different servers and nodes and all that? So, you know, Kubernetes has really kind of emerged as kind of this orchestration platform, if you will, right? However, you know, it's not without its challenges. I think, you know, networking and security have always been challenges of Kubernetes, especially when you want to federate data. But what about, the database itself? And what does this mean to, Kubernetes, especially with the nature of pods being ephemeral, or, they're gonna come up and down relatively all the time, right? Kubernetes originally kind of thought of for kind of these stateless workloads. What does it mean when you do need state? And I think with StatefulSets and some of the work the community has done, we've come a long way. But what does it mean when we want to actually deal with data that is, broadly distributed? I don't want all access to a database going through a single data center because it's a bottleneck and it's a risk, right? How do I actually spread that in all four corners of the planet, if you will, to meet latency, but also kind of provide survivability and this resilient nature of systems? And how do we do that in data? And that's really what we wanted to talk about here today. But let me take a step back and give you context of Kubernetes and kind of these things, right? And so I hope I don't have to tell everybody what a container is, but I mean, just at the highest level, a container really been around with us for, man, I guess, decade and a half or 2 decades now. Really the concept of a container, but really kind of popularized over the last 8 or 9 years by Docker and such. But really a container is basically an abstraction level that allows you to write an application once, but deploy it pretty much anywhere. And it just basically takes care of all the dependencies of the underlying system so that you can code and not have to worry about how you're actually going to deploy that software. But back in the day, we had to actually build our applications for Windows or for Mac OS or for Linux, right? We had different versions of our software because of all these dependencies. Well, it takes all that away and it abstracts things out, and it's really kind of ushering the dawn of this world of kind of microservices. How do we break down these large applications into smaller services like this get account thing, right? And so we can scale little pieces very easily and be API based and basically just communicate across multiple different services to pull together some sort of function. And so the container at kind of the lowest common denominator in this conversation is actually pretty important. But when I actually am deploying containerized services, I can have thousands of these. Even if I have 100, even if I have a couple dozen, it's still difficult to basically maintain and control all these kind of containers that are running out there. What do I want to SSL into every node and make sure things are up and running all the time, and spin things up and spin things down and look at the configuration and certificates and all. It's complex, right? So at the core, Kubernetes really breaks down into 2 things: a control plane, which basically looks at all the different pods, and a pod, which basically runs on a machine, which allows you to basically control that particular node, if you will, a server, right? And so basically, when it really breaks down to it, the control plane is making sure things are up and running and provisions things. And then the pod is the local piece that basically is communicating back to the control plane. And that's really the ultimate architecture. Now, there's some cool things we can do with the control plane. It allows you to set state for the cluster across multiple different services. In this particular instance, I have a blue, red, and I think that's green. Is that green, Cleeth, or is that yellow? I don't know.
It's yellow.
It's yellow.
It's
okay, blue,
yellow, yeah.
Kind of blue, reddish, yellow. These are 3 services. Say it's get account, say it's print something, say it's a login service, whatever. And I can share these things to lots of different things, right? And so what it does, it uses basically the brain of the control plane, which is etcd, to say, hey, look, I want to spin up 10 instances of this blue service. And Kubernetes is going to use the pods on these different servers and go spin up 10 instances. And it's going to spin them up in different nodes or different servers, if you will, make sure those things are up and running. I could then scale and I could bring up another instance. I could bring up, let's say, I want 8 instances of red, 8 instances of yellow. It's going to spin these things up, right? And it's going to make sure it's going to maintain that state of 10, 8, and 8. I can scale up real easily. It can recognize changes and I made in etcd and say, I want 12 of blue, I want 7 of red, I want 10 of yellow. Great. It's going to add this throughput, right? And it's add these services, provision them out for you. I didn't have to SSL into every machine and do this. This is basically going to take care of all this for you, right? It also is important because it recognizes when pods go away. So in this instance, the red server there went down. So I had, what did I have? Like 2 reds and a yellow there. And so those went away. And so Kubernetes is smart enough to know that these ephemeral workloads have died, but my state is now wrong. I only have 5 reds and I only have 9 yellows up and running. So it's smart enough to spin those up on another node and make sure that they're running, right? Pretty simple and straightforward. And that really is the gist, if I break it down into kind of the 2 things that Kubernetes does. A, maintain state. B, provide some sort of survivability, right? All right, so basically Kubernetes does two things. That's kind of what we walk through, right? So what about the data in these distributed environments, right? We talked about these issues before. Well, CockroachDB was really created as a database that was purpose-built and architected for this new world. You know, the origination of Kubernetes is something called Borg, really being the baseline of this. And Borg is basically the back end of Google. All the services in Google are running on Borg, right? And actually, you know, Google created a relational database for that new world that was distributed, and that was called Spanner. CockroachDB is a direct descendant or direct derivative, if you will, of Spanner, right? So Spanner is to kind of Borg as CockroachDB is to Kubernetes. This is a database that was purpose-built for that, right? You can spin up a node anywhere. We can point it at a cluster. It's going to take care of coordinating transactions. And just like Kubernetes, it's going to make sure that nodes and data is always up and available. And I'm going to walk through a little bit about how that actually works, right? There's some kind of special things we can do. We can tie data to location as well, but this was a database that was purpose-built for a distributed environment and basically for Kubernetes, right? And so we believe this is kind of the right combination if you wanted to start to federate data and have data live globally. Now, can we federate clusters? I think it's still a bit of a challenge. You know, there's some people out there trying to solve those problems today, but we can absolutely federate data and have that live in multiple different nodes across an entire planet. We're going to show you a little bit of that today. So with that, I'm gonna hand this over to Keith so that you all can see some of the basics here of how this works. So Keith McClellan, there you go, buddy. Make Keith the presenter. There you go, bud. It's all you.
Awesome. So well, we have two parts to this demo. The first bit is just kind of showing the survivability of CockroachDB running in Kubernetes. And then the second part is going to be moving just from survivability to a highly performant environment. So what we have running right now is a 9-node cluster of CockroachDB running in Kubernetes across 3 different data centers. So we have 3 small GKE environments running in US West 1, US Central 1, and US East 1. In this case, we're entirely in Google. One or more of these data centers could be in a different cloud provider. It could be in your own on-prem infrastructure. We could have decided to make only 2 of these 3 data centers Kubernetes if we had wanted. That's not what I did here today. But and you can see I'm running a little bit of load across each of these data centers. I have roughly somewhere between 150 and kind of 200 queries per second hitting each of these regions. Each of these regions has multiple nodes that we're going to watch. Now, performance right now, this is a completely unoptimized instance, not really all that great. We're gonna make some improvements as we kind of run through here. But the first thing I'm going to do is I'm going to kill one of the pods that is running CockroachDB in US East. And what we're going to see is over the course of about 10 seconds or so, the database recognizes that we have a node that's not currently responding. As a part of that, we're going to be monitoring for a period of time because sometimes a Kubernetes pod will become unavailable. If it rejoins the cluster within a period of time, we just get it kind of caught back up. If not, and I think the default timing is about 5 minutes. If we were to wait for 5 minutes, we would mark that pod as dead, and we would kind of actively start re-replicating the data. This is all while continuing to run load into the database. As you can see, maybe you can't see from that particular view, we're still running roughly the same amount of transactions per second into the database that we were before the pod died. There's a bit of a performance hit, of course, because we did lose some of our infrastructure, but our application continued to run. We're continuing to be able to process data from across all 3 of these data centers. I'm going to let that pod reinitialize now. And what we're going to see is it's going to rejoin the cluster and get caught back up. And we'll see a slight performance increase when that happens. So you can see that the node is no longer listed as suspect up top. We've caught up the under-replicated ranges. That's the shards of data that were being managed by that node that went away for a little while. And we're back up to roughly about 500 queries per second. So we took a little bit of a dip, but now it's starting to recover. With that, Jim, I'll throw it back to you for a couple of minutes, and then we can kind of move on to performance optimization here.
So let me just explain some of the things that happened underneath the covers of what Keith was talking through. And so what we saw was a cluster of nodes, each node of CockroachDB running in a different pod on a different server, geo-distributed across the United States. I think you had 3 regions here in the United States, right, Keith?
That's correct.
And, yeah. And so the data itself actually was replicated across those nodes. And so the database itself is actually dealing with where this data lives within that cluster. And we're going to show you some optimizations we can do in the next section. But in order to do so, we just need to give you a little bit of a background around how actually CockroachDB takes care of data underneath and what it means when it replicates and distributes data. We're actually writing data into the cluster 3 times. And we're doing so because, well, if a node goes down, I still have access to that data. So what Keith showed you was killing of a particular pod. Well, all the data that was written on that pod, be it whatever it was, whatever parts of the database, well, if that was just gone for a minute or 2, well, then I wouldn't be able to access that data. However, in CockroachDB, we have 2 other copies of that data living on different nodes or within different pods, different nodes of CockroachDB, and it's always being accessed, or it's always accessible. So this kind of native ability to be survived, or to this native ability for survivability, I guess is the native ability to survivability. Yeah. This survivable thing is really based on kind of how we write data to the cluster. Now, we can also do things like scale very easily. We add more pods and it's going to redistribute data. We're going to show you that as well. But ultimately, under the covers is a protocol called Raft. And Raft is a distributed consensus protocol that allows you basically, we use it extensively. And we've done a lot of work within the etcd/Raft repo of GitHub in terms of open sourcing what we do. But you know, our implementation of Raft is used within CockroachDB to manage basically replicas of data. If you think of the way that a table is broken down, we break it. Well, I'll show you in the next. I'll show you in the next in the next slide how that works. But if we think of a range of data, just think of a table or a part of a table, a shard, if you will, or maybe just a range. Well, we're basically writing this data 3 times, and there's going to be one of these copies that's basically in charge of the others. That's called a leaseholder. And basically what Raft is doing is making sure that it always has 3 copies, right? It's do I have enough here, right? Is my replica set complete? And if it's not, it's going to make sure that it is. So let's say I lose a node, it's going to make sure that I have this 3rd copy somewhere, right? And so it's a real critical piece of what we do. It's a really interesting protocol, and if you actually want to check it out, I would do some research on Raft. It's pretty awesome, right? But it's also helping us in the way which we actually distribute data across a cluster. So as I was saying, you know, each table in CockroachDB is broken down into ranges. So here we have a list of dogs. You can imagine this is a table called dogs. You'll see that all the rows, if this was all, you know, pulled together, Carl, Downey, Figment, Jack, Lady, Lula, Muddy, Petey, Pine Top, Sushi, Stella, Zoe, Z, I should say, that's all one table. What we've done is we break the table down. We order everything first, right? So you'll see it's in alphabetical order. And then we break down the table into these ranges, which are these manageable chunks that we can actually distribute and redistribute across a cluster, right? And so there's lots of science in that. You can actually configure how large that's going to be. You can actually say how many replicas we're going to be. But what we're going to do is when we place data into nodes within a cluster, so here's 4 nodes here. You can imagine these are all in one region. Basically, we're going to now distribute that data across various different nodes within the cluster. And we can do so that each of the ranges can survive the loss of a particular node. We're also going to do so because, well, we can actually place data based on what we want to survive too. I want to make sure I survive a regional failure or a disk failure, right? In this case, we're doing it for a node failure. And you also see that we optimize how these things were placed based on storage. So how much data is living on each particular node, which is kind of cool, right? And so we're writing data in triplicate on the back end. And basically, there's no like control plane doing this. It's just the nodes themselves and Raft that's coordinating all this different stuff, right? So the database is just dealing with this whole distribution of data, right? And so we can also place data based on load. So let's just say there's a range of data. Let's say everybody really loves this muddy record. Everybody wants access to that, or it's writing it a lot, whatever. And there's an extensive load. There's a hot spot in my table, right? We can actually separate out these ranges of data off into nodes that aren't used as much as others, so that we can optimize for load as well. So not only optimizing for storage or survivability, but the database is smart enough to actually take these heuristics and these real-time usage metrics across a table to basically segment off, or to weight off like a particular range of data, so we can actually get better performance, right? And so it's pretty cool, especially when there's tens of thousands of ranges or hundreds of thousands of ranges going on. The database is pretty intelligent enough to actually deal with these sort of things. Now, the last thing we can do is we can also take these ranges and tie a range of data to a particular location. So I could take all the data that's supposed to be in the EU, have it live on servers that are in the EU. I could take all the data that's supposed to be in this blue range. I could have that all live on the East Coast, if you will. Whoa, man, I think my colors are wrong. These guys should be yellow up here and this should be red. So excuse me here, I have a slight problem here. But basically what we're doing is we can use a field of data within that table to basically segment data. And what we're doing is we're allowing for this thing called Geo Partition. Now, we do Geo Partitioning for initially because of performance. When you have a distributed database and you want people to access data, all nodes within the database itself are a single consistent gateway to the entirety of the data. Now, if I asked one node for a piece of data and it had to go to Sydney every time to get that, and I'm living here in New York, well, there's a pretty long latency for that response to come back. So wouldn't it make sense to have a copy of that data here in the United States? Well, yeah, we can do that. We can have maybe one copy in major geographies, but we can actually say, I want all copies of that data to live here in the United States, so that I don't have to worry about getting quorum when I write things and these other things that are actually pretty important in the database. And I can have that data kind of follow a user. Now, that's important for performance, but it actually has huge ramifications for things like GDPR and jurisdictional control of data, because now the database itself is actually tying data to a location. Now I can name any node whatever I want and have that data tied to it. And so it's a real critical piece and kind of one of these nice pieces. But Raft and replicas and distributed consensus is basically what's allowing us to do a lot of this stuff. And that's all underneath the covers, right? So what happens when I add a node? So let's say I had 4 nodes. I had node 1, 2, 3, 4. I added a node. The database now, there's no control plane. The database is just smart enough to know, like, hey, somebody pointed this new node. It's a TLS connection. They pointed at the cluster. And it said, hey, it's smart enough to know there's a new node. The database is smart enough to actually now move replicas into this new node to balance things out. Now, all of this is done automatically. So if you're familiar with sharding of a database, well, no more manual sharding, no more dealing with, I'm gonna have this part of the database live over here. Like all this manual craziness that goes along with sharding is completely replaced with this automated way. And it uses Raft to do that, right? And so I just sharded a database, simply spin up a node. If I have a TLS connection, I point it at the cluster, and it's gonna redistribute data and rebalance that. So you can imagine I could start scaling the database very easily, right? I can also deal with failure. So there's no more need for these kind of active passive systems for failover for immediate access to data. If you think about like the 2 data center problem, I have an active and a passive system. Well, with CockroachDB, everything is active. I have copies of that data all over the place. So if the leaseholder or the data that I wanted was living on this node that went away, it's node 3 here, well, I have 2 copies of that data living somewhere else. And so RPO, RTO go to 0. Right? I can actually still access that data, right? And the database is smart enough to understand, like, wait a second, I'm under replicated. That's what happened in Keith's demo, right? Remember the thing that said under replicated ranges was at 18? Well, there were 18 ranges living on this node that went down. And basically what it was doing, it was redistributing that data to other nodes, because that node, if that node had never come back, it would have basically made sure that I had 3 copies of that data all over the place, right? And so the database is smart enough to kind of give you this effortless scale, right? That no more need to manual shard, but this kind of ability to kind of give you this kind of bulletproof resilience, so that your data is always going to be available without any extra configuration, any extra servers, any extra software resources. it's all kind of inherent in the database, right? And so that's kind of the two key points of that. So I want to get back over into Keith and show a little bit more of this in CockroachDB. So Keith, you're back, buddy. Hold on, let me get you shared.
Great. So
what did I miss? Did I miss anything there? Was that all good?
That was great. No,
Oh.
so by default, we're going to distribute these ranges of data as in as highly available a configuration as possible. That's not always the ideal configuration for any particular application. You mentioned regulatory reasons. There are also performance reasons why we might want to make some changes. So this application we're running right now, it's called Mover. It's a simulated ride-sharing app split across 3 cities, New York, Chicago, and San Francisco. We didn't do any performance optimizations. I was just showing you the database running the way it would kind of make naive decisions. So over the course of building an app, of course, you're not going to just leave the defaults. You're going to add some performance optimization. So we're going to kind of see what the impact of just some basic performance optimizations that don't impact survivability, how those change the performance of the database. So I'm going to start by setting some partitions on the tables and building some secondary indexes. So one of the things that Jim, I think you talked about was leaseholders. Leaseholders are an interesting concept because they're kind of the first among peers for those replicas. So each replica has a leaseholder. It's the arbiter of rights to the system. And reads to the system, right? So what we're going to be doing here is we're going to just kind of change the default location for the leaseholders to be where any particular part of the data is most likely to be interacted with. So as you can see, kind of one of the first initial changes is because I'm partitioning the table in a more finely grained way. The replicas per node is going to change because we're going to change how we're sharding the data. So the actual ranges are going to change. What we're going to see as that change goes into effect, once those replicas have started moving to their final locations, our actual throughput for the database is going to increase. So we started somewhere in that 400 to 500 total queries per second range. We're now well over 1,000 queries per second. And the only changes that I made to the database were some DML changes, some DDL changes to the database. So I set some zone configs for New York, Seattle, and Chicago, and I changed the partition of a bunch of tables here. So nothing more than a couple of commands that the DBA can run just to kind of change how we're distributing data across the database allowed me to more than double the query performance of the cluster from a queries per second perspective. Or also our P99 latency, that's our worst case latency in the system, is now down to roughly 40 milliseconds from, we were running at somewhere in the vicinity of 400 to 500 milliseconds. Now we're in the 30 to 80 milliseconds, which is fast enough for real-time application use. But that's still not good enough. We have,
hey, Keith, really quickly,
yep.
You mentioned something called a zone configuration, and can you just explain what that is and where it's applied?
Yeah, so a zone configuration is a data definition extension that's specific to CockroachDB that describes how we want to partition the data across the physical topology of the database. So when you're talking about a distributed database like CockroachDB, the actual physical layout of the data across your nodes is just as important as the logical data layout of the data in your system. So the zone config specifically is us describing how we would like to physically distribute the data across the system. Does that answer your question?
Yeah, so in this case, I mean, we applied it to, I forget which was the table that we applied it to here.
I think we actually applied it to all of the tables.
Okay.
So there are 5 tables in this particular, 6 tables in this database, and we made a change to each of those 6 tables. So The effect is you can see that I set some partition structures that say have the New York go follow the New York rules, have Chicago records follow the Chicago rules, have the Seattle records follow the Seattle rules, and then the actual zone config, that's these alter partition statements here, that actually describes what I want to do with each of those partitions. And while this particular partition is pretty coarse grained, we did it at a city level, we could have done it all the way down to an individual record ID level if that was necessary. So any element that can be included in the key, in this case we have ID and city in our primary key, any item that's included in our primary key can be used as a partitioning constraint.
Interesting. And so what table was this on, Keith?
In this particular table, looks like this is the vehicles table.
Okay, cool.
But we have similar configuration to the users table as well, based on where we expect them to do the most of their transacting from.
I guess I ask you, I mean, it's pretty important, right? You can do it at the data that needs to be geo-replicated or partitioned to a particular location is where you want to do that. Like, you don't need to do that for promo codes. You just want that available everywhere, right?
Well, so promo codes, that's about where we're going to start looking at this a little bit differently, right? So promo codes, those don't have a geographic constraint. What we actually want is we want to have some, we want to make sure that all of the promo codes exist in all of the geographies so that we have the fastest possible reads. There aren't very many writes to the promo code table. We're not generating hundreds of promo codes a second. But we want to make sure that everyone has fast local access to the promo code. So what I'm going to do next is actually apply partition duplicate indexes, which is a strategy that we use for creating a local replica, guaranteed consistent replica of the data that we can use for super fast reads. That's going to bring our P99 latency down quite a bit more as well. One of the interesting kind of side effects of this is that our slowest queries right now are all going into the promo codes. So they're either rides that we're leveraging a promo code, or they're actually users trying to read from a promo code. Everything else is pretty fast right now. So we're going to go ahead and quickly kind of apply that partition duplicate index. So I'm going to go ahead and kick that job off here in the back end right now. We're going to see our performance. So you see we're creating some changes to an index. There's going to actually be 2 new indexes created and 3 new zone configs applied. From a database perspective, oh, clicked on the wrong spot. User promo codes now has partitions that didn't have before. And those partitions, rather than applying them from, promo codes, not user promo codes. So rather than applying these, a partition where we added, say, a city to the primary key, what we're doing is we're creating covering indexes that exist in all of the regions so that we have guaranteed local consistent reads. We take a bit of a write performance penalty because we have to update 3 indexes anytime a new promo code is added, but this table is relatively small, so the penalty is not real large. What ends up happening is our general performance gets a lot better. So we'll go ahead and take a look at kind of our P90. Our P99 query performance is a little bit better. Now we're getting closer to kind of the 20-ish millisecond range. This is going to continue to improve over the next minute or two as the indexes are built. But our 90th percentile went from 30-ish milliseconds down to sub 10 milliseconds. That means for 9 out of every 10 queries that are being executed against the database right now are executing in less than 10 milliseconds, and 99 out of 100 queries are being executed in roughly 20 to 40 milliseconds. It looks like we still have 1 or 2 nodes here, node 1 and node 9, that are still building the index. They'll get caught up here in a minute or so as well. And the net effect of this is we can create a distributed application with a common data plane that has roughly equal performance regardless of where you're interacting with it anywhere in the country, which is a very challenging thing to do historically.
Awesome. And so basically at the table level, you have lots of different tiles that you can play with, Keith, right? And I think, you know, let me ask an odd question here. This didn't come up yet, but you know, say the promo codes, say there's like a new field, like I want promo codes that are, you know, that are regional, right? And there's a new piece of the promo codes that is going to want me to distribute it in different ways. You know, how would I go about that? Like, let's say I'm going to change the schema to the promo code table, and then I want to actually change where these things actually live because I want promo codes in the U.S. and promo codes in, just say, Europe. How does that work? And I guess I'm leaning towards, you know, how do schema changes work in CockroachDB?
So schema changes are online. So what you would need to do to apply the change you described is we would need to add a characteristic to the primary key for promo codes. So if we go back into promo codes, you see that there's no kind of a location, right? But in the user promo codes, these are the promo codes that are actually used, there is, right? And you see how you get these alter partition statements, and then we kind of create some indexes. We would do an online schema update. So we'd update the primary key. This is something we can do without any kind of a ETL or downtime as of 20.1. So we would add a field to the database that gave us a geography. We would then include that field in the primary key. And then we would apply the same type of placement rules that we applied to the other tables to this table to meet that requirement.
So it's simple as a change to the DML, and you have basically a schema change happening in production without downtime.
That is correct. Now there will be a bit of a performance impact depending on what percentage of queries interact with that table. That you will see some percentage performance decrease while we're physically changing how the data is laid out on disk. But that's still far superior to taking an outage, right? Most DBAs can pick a slightly less busy window and use that time to apply these types of online changes.
Yeah, I mean,
and that's what we would recommend.
The database down is the whole thing here, right? I mean, you're up and running, you're in production, and you may have a slight impact on performance, but honestly, it's better to do that 11 at night than at 2 in the morning and have the whole system down for 3 hours or 2 hours or even a half hour, right? I mean, you're losing transactions at that point.
Yeah, a lot of systems that are required to be up through those types of schema changes, they do these complex handoffs. There's risks of having to kind of manually remediate transactions that didn't get replicated properly. There's always hiccups with that. It's the same type of hiccups that you would have if you were trying to do some sort of a DR strategy. We're highly available to the point where we could lose in this configuration that I have set up here right now. If I took out an entire region, if I lost US East 1, US Central and US West would continue to operate, and US East 1 users would be able to operate against the 2 remaining data centers without losing any transactions. We can guarantee consistency in that scenario. Trying to do kind of disaster recovery with asynchronous replication, you run into the same types of problems with trying to do offline schema updates, where you still need to maintain uptime as you do in a kind of a DR type of a scenario.
Right. Cool. So you basically have the double here. You have both the database that's going to survive anything at the data layer, but then you also have Kubernetes underneath, which is basically making sure that the database is up and running, right? It's almost like self-driving database, like for real though.
Yeah, I mean, it's to the point where I had to do unnatural things to stop Kubernetes from restarting the pod that I deleted.
Right.
to demonstrate a down node. It's if you were to just go and do a pod delete, kubectl delete pod name kind of a command, by default, Kubernetes is going to restart that pod. CockroachDB might notice that the pod was down for a handful of seconds, but from an operator perspective, by the time an actual DBA went and looked at an error that they got alerted on, the system would have healed itself, which
Right.
definitely allows for DBAs to focus on kind of higher value tasks than just kind of the care and feeding of individual servers and instances.
Well, let me ask a question on that. And there was a question about this a little bit earlier. Thank you everybody for the questions, by the way. If there are any more, please do throw them in there. I think I answered one of them publicly, but there's been a couple more. Keith, in the instance that a pod does go down, and you had mentioned this a little bit earlier when the question came up. I'll just throw it in now because it fits. How does CockroachDB come back from that, right? Because as a pod goes away, it's ephemeral, right? Everything goes away, right? How does Cockroach deal with that? Because this is data. I mean, this isn't like some ephemeral workload, some stateless thing, right? Like how do we deal with that?
Yeah, so there are a couple of configuration options. The most common one is to use StatefulSets, just generally how we recommend running CockroachDB, where we're going to attach a volume to your pod, and if that pod restarts, when the pod restarts, we're going to reattach that volume. Now, after an individual node or pod has been out of the cluster for 5 or more minutes, the volume is no longer up to date enough for us to just kind of catch it up via a snapshot.
Right.
That's when an operator might actually have to get involved. Generally speaking, we would recommend deleting that pod and recreating a new pod with a new stateful set and letting the database kind of self-heal, although there are certain circumstances where you may not want to do that, and in which case there are certain commands you can use to kind of force a pod to be allowed to rejoin, even if it's been out of the cluster for 5 or more minutes. Really, the question about which one is the better pattern has a lot to do with the amount of data and the rate of data change over the period of time that pod was removed from the cluster. There's no one right answer that kind of fits everybody. Generally speaking, Kubernetes is self-healing enough that unless you lost a pod host and you lost the volume that was hosting that stateful set, more likely than not, Kubernetes is going to bring up a replacement pod with the new that's mounted the existing stateful set faster than we're going to remove that quote unquote node from the cluster.
Right.
So it'll act in a self-healing fashion in that regard.
So I mean, it really basically comes back to how much you're willing to withstand in terms of resource and optimization from that point of view, ultimately, right? I mean, it's like, yeah, I think we can just rely on stable sets. In certain cases, those don't even work. So it's a little bit more of a hard reset of a particular node. Doesn't matter. All the while, the database is still accessible, right?
Database is still accessible because we work on a quorum. As long as we have 51% of the replicas available, the data is still available somewhere else in the cluster.
Right. Yeah. And in this case, what we're talking about, it's like 2 of 3, right?
It'd be 2 of 3, and so we'd be good to go. If there were concerns about being in a single point of failure mode, if you lost a single node, then we would recommend doing, a 5x replication strategy. Some, globally distributed clusters where we're running across 6, 7, or 8 sites, we might recommend a higher replication factor. All depends on really kind of what scenarios that this environment needs to be able to survive. So we guarantee consistency, and by the nature of us being a multi-node database, we manage for partition tolerance. So the way that we have high availability is via this quorum calculation, and you did a great job describing how Raft and leaseholders kind of manage this for us. So if we need to be able to survive, say, 2 full data center outages, right, then we can design for that by setting ourselves up for success and saying, hey, we need to have at least, if we need to survive 2 full data center outages, we need to have at least 5 sites available. And we need to have a replication factor minimum of say, I think it's 5 in that scenario. And kind of following those patterns and making good design decisions to allow us to be able to guarantee availability in different failure scenarios.
Yeah, so interesting. You said a couple of things I just want to key on, and this is my own questions actually. You talked about some customers doing multi-site, multi-region basically. I mean, correct me if I'm wrong, but I mean, if they're running on Kubernetes, they're basically managing each of those Kubernetes clusters locally, but then managing the data globally. Is that correct?
Yeah, so each Kubernetes cluster would be individually managed, and then we would require some sort of network peering across those environments.
Right.
That is probably the most challenging thing to do in a distributed environment is to manage the networking.
Right.
Depending on the sensitivity of the data, we could send it over the open internet. That's what we're doing in this demo. We're using encrypted TLS to transport the data, and we're just kind of shipping it over the open internet. Not maybe the most performant solution, but it is probably the easiest thing to set up for a demonstration like this. If I were to build this for production, I would do VPC peering, or I would do some sort of VPN tunneling to kind of peer my networks across sites. All nodes in a CockroachDB cluster have to be able to talk to every other node in the CockroachDB cluster, but they don't all have to be close together, right? What is important is that a majority of the replicas kind of be reasonably close enough together that we can do relatively fast commits on writes, right? So we wouldn't recommend one data center in the US, one data center in EMEA, and one data center in APAC, and have that be your entire CockroachDB cluster, because your mean round trip time between your closest 2 data centers would be measured in hundreds of milliseconds. Whereas if you need to do a worldwide cluster, maybe you would do 9 data centers. You do 3 in the US, 3 in EMEA, and 3 in APAC. And then we would do some of these performance optimizations to make sure that 51% or more of our replicas kind of stayed co-located to the region that the data started in, or in EMEA, maybe we would pin that data there completely. Now we could still set it up so that we could have relatively fast reads by continuing to replicate to those other data centers. But we want to make sure that that we had sufficient replicas in a relatively close geographic window. And by relatively close geographic window, we generally talk about wanting to have our data centers 20 to 40 milliseconds apart, which is what we were doing here today with US West, US Central, and US East, to kind of manage for both performance and availability.
Right. Yeah, I mean, it's just an interesting topic. I mean, it just goes to the very unique capability that we're able to actually distribute data across multiple different regions like that. I think it always has its complexities, but all very good. So, all right, well, cool. Anything else, Keith? I want to wrap it up with a couple slides, and then I think there were a couple more questions I could take at the end.
Yeah, I will switch the presenter back to you.
All right, there we go. We are rebalancing. So I guess in the end, this is a database that was purpose built and of a natural fit for Kubernetes. It's fairly easy to deploy. Using a Helm chart. We want to talk about operators. There's a question about that, but and then using storage class. That's how we mount volumes using the storage class. So via BV claim. And actually, funny enough, that there's 2 questions in here that I wanted to actually talk about. And we'll just take them here while this stuff is on the slide, actually. Do we have an operator for Kubernetes, Keith?
So we don't currently have a supported operator for Kubernetes, although we are moving in that direction as a company. Because we're such a good design fit, pattern fit for Kubernetes, we've gotten away with not having an operator for quite a long time, actually. Our Helm chart does kind of pretty much everything you would need to be able to get a database up and running, get started, and from a a performance production config, we can generally manage that stuff with a static config. We are starting to see customers who are trying to manage multiple CockroachDB clusters in a single Kubernetes environment, or customers who have some kind of day two operations type of workflows that could be easier. And because of that, we are kind of starting to work on an operator that we're hoping to open source and share with the community here, later this year. But you don't need an operator to run CockroachDB on Kubernetes. It's not a requirement to run it. It just makes kind of some of the administrative tasks easier.
Right. Yeah, I think it's one of those things where it's a natural fit. So what's the point, right? So, well, cool. And then the last thing was, as somebody was asking about how does storage work, if there's storage within a pod, or how do you, because the database ultimately stores data, I'm paraphrasing here, how do you attach data to each node?
Yeah, so we're going to use persistent volume claims using StatefulSets, right? And the easiest way to do that is using a storage class, right? There are other mechanisms that were supported. Someone wanted to set up daemon sets, or wanted to do kind of statically linked PVs, we could do that. You could also set the database up to use ephemeral storage, in which case then you probably would want to increase your replication factor. Just so that, because we're going to manage replication of the data across the nodes, but
right.
Because you wouldn't have any persistence if a pod failed, you probably want to make sure that you had more replicas, because that, the pod failure, like a temporary rolling pod failure, would or an upgrade would take a lot longer than it would otherwise if you're using persistent volumes.
Right. But it's all natural, basically, the Kubernetes framework to basically do this whole thing, right? And I think checking out the storage class and understanding what that means in Kubernetes is such a critical part of understanding how these sort of things work, correct?
Yeah, and generally we support any pattern that dedicates storage resources to each CockroachDB pod. So
right. You could use Rook, you could have distributed storage for that matter, right? I mean, Jesus, right? So
yeah, I mean, there are performance constraints for any of these decisions, and they're ones that we would recommend for production, and ones that probably are only really acceptable for for a dev or a test environment. But that's kind of where our black belt experts kind of come in and help folks figure out what the right thing to do is for their specific environment.
Well, cool. And I'm going to actually end it there. So our black belt experts also write a whole lot of really great docs as well. And I've worked at a few open source companies, and just an even regular enterprise software, like our docs is really phenomenal. There was a question earlier from somebody in the chat, and they were asking, is this sample application, the mover application, available? Absolutely. The Git repo's out there, but you can actually access, benchmarks for TPCC, for YCSB, for some others. If you wanted to do benchmarking of us, you want to run an application, just go check out Cockroach demo, and it's actually shipped within the binary, all this stuff. So you can actually go out and do a lot of this stuff yourself today. But I would check out our docs, and they're pretty valuable. They are verbose, they're complete, and I think they're extremely valuable. We get compliments all the time. So kudos and shout out to that team, because they do some really great work there. So I made it through all the questions that we had through the thing. So somebody's asking, can we please share the slides? Yes, absolutely. We'll definitely share everything post event. But the slides and the recorded session will definitely be available. But I'll let you guys that. Last two things, if you want to go check out a little bit more about what we're doing with Kubernetes, go check out cockroachlabs.com/Kubernetes. Some of the stuff is there. And then also, we're going to have, Keith and I are going to be on the phone again next week talking Kubernetes on June 3rd for 60 minutes. Go check out our website, cockroachlabs.com. Under resources, you go check out Community Tech Talks. Register for that if you want to actually access some more questions. We'll get a lot more industry experts on there too. But that's next week. And then if you want to go try Cockroach today, well, you can actually go do it. Just if you can go to Cockroach Cloud, You could spin up a cluster. You can have a connection string. You could write your own apps against that today and try it all for free, a full version of CockroachDB. So, we implore you to go there today, spin up your own cluster, play with it, build out a hello world, or download the bits, our community, our core version, and install it locally. There's some really great guides and how to do that. But you can actually go and play with all this stuff right now if you wanted to. So with that, I'm going to hand it back off to our organizer, and we are going to end this thing 3 minutes before the top of the hour.
Perfect. Thank you, Jim, and Keith, for that wonderful presentation. I would also like to thank Cockroach Labs for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Thank you and have a great day.